All right. So, without further ado, let's start our 5-minute talks.
So I'm going to present joint work with Francis Bach, realized over last year. As in the previous talks, we are concerned with supervised machine learning, where we have training data, x and y's, and we want to build a predictor function f, so that for a new unseen data, f of x approximately equal to y, so that's the goal of supervised machine learning. But in this talk, I will present results about the convergence of gradient descent-based algorithms for 2-layer neural networks. So for this specific structure of neural networks, we have this sum structure where the predictor function is a sum of m simple functions, where m is the number of nodes in the hidden layer. And each of these simple functions is actually this function where, with parameters wi, which are the input bias, input weight, and output weight corresponding to one of the neurons. So we consider a statistical setting where the input, the data distribution, we assume the data is distributed according to some probability distribution, x and y. We choose a convex loss function, and we want to minimize the expected loss, which is the generalization loss. And we want to find the best parameter w for this function. It's known that it's a hard problem, even though we have just 2 layers in this simple neural network. There are spurious minima, and even in favorable setting. So we want to understand, even in favorable setting, and even in some slight overparameterization setting. So we want to still understand what gradient descent, why gradient descent performs good on this problem. And to do this, we will look at a specific idealized dynamic, which is somehow a mean field analysis. So we look at the training dynamics, for instance, with stochastic gradient descent in the small step size limit. In that case, we'll obtain continuous path in times for each of the hidden of the parameters for each neuron. This is this dynamic. Then we can define the empirical distributions of these neurons in the parameter space that will evolve in time. And this gives a measure on the space of parameters. So for instance, here we have an illustration of each red dot represents a neuron that evolves in times. And this is the training dynamic for this problem, 2-layer neural network. With this description, we can take the limit when the number of hidden units goes to plus infinity. In that case, we obtain a dynamic which is Wasserstein gradient flow, as Pratik has talked about before, but it's in a very different context, so don't mix the two results here. This density is the density over the space of parameters represented by all the neurons. And we see that when we add more and more neurons, there will be, and actually we can show that there will be some non-trivial limit dynamics. This limit has been studied in several papers over the last year with various goals in mind. And here, we have used this point of view to give some global convergence result for gradient-based algorithms. So in a very informal way, you can find a rigorous statement in our paper. The theorem is as follows. This idealized dynamic, so in a small step size, large data set, and large hidden layer regime, asymptotic regime, the 2-layer neural network, if it is initialized with sufficient diversity, it converges globally. In that case, it means that it attains the best possible generalization over all possible hidden layer sizes. So here we meant sufficient diversity because it's a non-convex problem. We know that there are some spurious minima. We need a condition on the initialization to avoid this local minima. We don't have noise in that setting, actually, contrary to the previous talks. So we need diversity. This condition on the initialization is this diversity, and it's satisfied, for instance, for randomly initialized neural networks. Then this result covers highly nonlinear dynamic and also cases where we have regularization terms. So it's different from the previous talks also, where in the infinite width limit, the neurons stopped moving, essentially like they moved very little. Here, this covers dynamics of this kind where the neurons in the parameter space can have a large movement. And intuitively, this result is proved by showing that the more neurons we have, the more we are able to avoid the local minima. And in particular, the way our proof goes is that in the infinite width limit of the dynamic, all the local minima are avoided, and the dynamic converges to global minimizers, as is meant here. So I think this is the end of my talk. We have this paper with these results, and here a note where we explain also the relationship with other convergence results that you have seen today or in the literature. Thank you.
Oh. Hi, I'm Leo Karakida. This is a joint work with my collaborator, Shotaro Akaho and Shunichi Amari. We are interested in the Fisher information matrix of neural networks. The FIM play a fundamental role in machine learning, basically because it determines the geometry of parameter space. Moreover, it is equivalent to Hessian of the loss function under certain conditions. So the FIM also determines the shape of loss landscape. So FIM is a fundamental quantity. However, its theoretical understanding has been limited so far. Most theoretical studies are based on special type of shallow neural networks. So in deep case, in general deep neural networks, there are almost no theory. In contrast, empirically, several researchers have reported that many eigenvalues of the FIM are close to zero, like this, while the edge of the eigenvalue distribution may take a very large value. So we'd like to quantify this type of statistics in deep neural networks. To analyze this, we suppose fully connected deep neural networks with random Gaussian weights and Gaussian biases, and suppose sufficiently wide deep neural networks. Such models are theoretically tractable by utilizing the framework like mean field theory or random matrix theory. And we also suppose the number of output units in the last layer C is a finite constant, and training samples are generated by also Gaussian. In this setting, we found that some basic eigenvalue statistics are analytically tractable. For instance, let's say the average of the eigenvalues. This becomes like this form. Cap1 is a coefficient composed of so-called order parameters. These variables are obtained in mean field theory, but this is not mean field approximation. This is a regular result in the large M limit. But anyway, the point is this average is of order 1 over m. So in the large M limit, this average is very small. It suggests that most of eigenvalues are close to zero. In contrast, we also found that the maximum eigenvalue is of order m, so very large. By definition, FIM is given by the form of outer product between derivatives. So it includes averaged shift of the vector, in this case, O. In this case, that is derivatives. And in usual setting of deep neural networks, this shift is non-negligible. So this type of pathologically large lambda max appear. And this lambda max is helpful in practical applications with gradient descent method. The lambda max determines an appropriate size of learning rate for convergence to the minima. One can see this type of necessary condition. So now we have an analytical evaluation of this lambda max, so we can estimate a good learning rate for convergence. So in summary, we quantify the pathological spectrum of the FIM. eigenvalues are close to 0, while a small number of eigenvalues take large value, very large value. Our future work is extend our theory to other architectures and clarify how to avoid such pathologically large lambda max. Some normalization methods or scaling of parameters may be helpful to avoid or alleviate such large eigenvalues. That's it. Thank you.
All right. So we have time for a couple of questions for the three speakers. All right, maybe let me start. So from an outsider perspective, right, so I see that there are a couple of eigenvalues which kind of are special, or there are just a few that survive. Can you give any interpretation to these eigenvalues?
Of the metric. Or
Yeah,
for
of the
instance,
Hessian.
in the case of Hessian metrics, they are negative eigenvalues, but the empirical Fisher matrix, that is a Gaussian Newton approximation of the Hessian, is a positive definite matrix, so no negative matrix. That means, for instance, in the case of loss landscape, such local minima with non-negative eigenvalues are just local minima, not saddle points.
So, yeah. In our case, you have this neural tangent kernel, so you can look at the PCA of the data that you have with respect to this neural tangent kernel, and that gives eigenvalues. And these are governing the convergence of the neural network during training, how fast you go to minimum loss.
So let me just make a comment. So if I understand correctly, NTK and the Fisher matrix are dual to each other in the sense that the NTK is like JJ transpose, and then the Fisher is J transpose J. So in that sense, the eigenvalues are exactly the same. And so what seems pathological in one sense, where you're fixing maybe the data size and you're letting the width go to infinity so that the Fisher is like super large, but essentially the effective spectrum is limited because if you take a dual matrix, NTK is a finite size matrix, so the spectrum can be at most of that rank, right? So is this still pathological if you look at it this way?
But in the case of neural tangent kernel, parameterization is a bit different from the usual parameterization,
That's true.
So the large eigenvalues can be scaled to order 1.
Is that
order
true?
1.
Is that true?
Yeah.
Okay. Yeah.
So that's a good point. Actually, that's how we invented the neural tangent kernel. We were trying to study the Fisher information matrix. And then we found that it was useful to understand training. So we didn't continue in that direction.
Nice.
Yeah.
Okay.
I have one question to the last speaker, Ryo Karakida-san.
Right.
So when you take a statistical neural network and also the summation of weights, so how did you determine the distribution size or the width of the weights? And does it, if I change it, then it may change your robust result?
So dependence on basically the eigenvalue distribution has two populations. One is bulk and one is edge. And edge is we don't know the variance of each population by our framework theory, but in experiments the variance of edge is very large. but we don't know. Maybe of order 1, but maybe depend on the wise. But in experiments of order 1.
Okay, I cannot see any more urgent questions, so let's thank all 3 speakers again. And we'll start the next talk by Sho Yaida.
Hi, I'm Sho from Facebook Research, and I'm going to try to summarize my paper that will be presented at ICLAIR this year in 5 minutes. Okay, so what I did in that paper is basically that I studied the dynamics of stochastic gradient descent from physicist perspective, and then derived some relation called fluctuation dissipation, and then further use that to better guide the training schedule in SGD. Okay, so here's what you often see when you train the model but using SGD. So here's like loss as a function of time, which is like energy as a function of time. And then like it kind of decreases and then plateaus. So if you see this as a physicist, then like you might think that the first part is like out of equilibrium state. So you pour the data into the model and they learn the pattern. But at one point it plateaus and that's like equilibrium state. So if this analogy is correct, then like you can especially like in a water case, that it comes with a bunch of stochastic fluctuations, like water molecule jittering around and pushing the pollen. So and then Einstein looked at this and like found this fluctuation dissipation relation. So the goal is that maybe we can come up with the same type of relation for SGD. And what should we do? So like, and we can. So what you need to do is just make only one assumption, which is that you assume that the SGD sampling is governed by some stationary distribution at long time. So you run the SGD, it runs to sample from this stationary distribution, which you can think of this like pond in the landscape. So this is loss function as a function of model parameter, and you see some sampling from this ponds. And like especially like in my work, I don't have to make any assumption about the form of the loss function. Like it doesn't have to be quadratic, and then also the noise doesn't have to be Gaussian. We don't have to pass on to SDE. So it's just one assumption, and then you can derive some exact result. So I won't go through the details, and you can just read my papers. So this is one example of the relation you can derive, and the bracket just means the basically thermal ensemble average, and this is the exact relation. So like any stationary distribution should obey this equation. And further, like it's pretty easy to measure this on the fly. Like when you do the simulation, like it's something that you measure anyway, so you can just keep track of that and then check whether this is true or not. And especially like this can be used to set the adaptive training schedule. So this equation holds only at equilibrium, at which point you should like change your training like hyperparameters. So here's the the precise algorithm. So you basically keep measuring this left-hand side and right-hand side of the equation, and then like check that whether it matches or not. And if it matches like up to like 1%, then now is the time to decrease the running rate, because if you plateau, there's nothing to do at that running rate. So maybe you should go lower. And basically I tested this and it works. So okay, so this is basically what I did. So study dynamics and then prove something and then do something better for the machine learning. And if you're interested, then please talk to me. Thank you.
Right. Next speaker is René Vidal.
All right. So I'm going to be speaking about the connections between optimization and physics, or more specifically, the connections with dynamical systems. So this is an area that's emerged over the last 3 or 4 years, and the idea is very simple and interesting. You begin with some optimization problem. You take some optimization algorithms, such as gradient descent. You compute the continuous limit, and that gives rise to some dynamical system. And now the question is whether there is any relationship between the two. For example, is the convergence rate of the discrete algorithm the same as the convergence rate of the continuous algorithm? Or can we use the continuous algorithm to explain some of the stability properties of the discrete algorithm? But you can actually do more. You can take, once you have a continuous dynamical system, there may be different discretizations. And it could be the case that different discretizations lead to different algorithms than you had started with. So the question is how to do that. Now, I said this is the last few years, but actually the first instance of this dates back to Cauchy, 1847. And we should all know about this. So you begin with some unconstrained minimization problem. You take an algorithm such as gradient descent. You take the continuous limit. And interestingly, if the function is convex, you can prove that the convergence rate match. So 1 over k for the discrete, 1 over t for the continuous. And recently, work by Boyd, Candes, and then followed up by others, thought about the accelerated gradient descent from Nesterov. That was a very popular and very useful method in various instances. But the acceleration, the reason why it could be 1 over k squared instead of 1 over k, and what that rate was optimal, remain a little bit of a mystery. And the question is, how can I accelerate any algorithm? So what was very interesting of their work is that they figure out that if you take the continuous limit of Nesterov, it gives rise to a second-order differential equation. It's time-varying coefficients, as you can see in here. And what was also very interesting is that, indeed, they were able to show that the accelerated gradient flow also is 1 over t squared, which matches the rate of the discrete algorithm. So the literature so far had focused on unconstrained and convex problems. And so what we've been doing is looking first at constraint optimization problems, typically the sum of two functions related by a linear constraint. There are lots of algorithms to do it. One of the most popular is the ADMM algorithm used in various instances. So you can take the continuous limit of ADMM, and what you get is something that looks very much like gradient flow, except that you just have this matrix in front of it that emerges from the linear constraint. You can also come up with accelerated versions of ADMM by using exactly formulas akin to Nesterov inside the algorithm. And in that case, you get this differential equation, which is, again, the same as what you would get for accelerated gradient flow, except that you've got this in front. And by the way, now you can use Lyapunov stability to analyze the stability of the trajectories, and you can also derive all of the convergence rates, and they match. So 1 over k and 1 over t for ADMM, and 1 over k squared, 1 over t squared for the accelerated version. So this is, again, in the case of convex functions and that are differentiable. So this can be extended to the non-smooth case. The only difference is that you have differential inclusions rather than differential equations. That brings a lot of problems because now the solutions to the differential equations are not unique. So one route is, and we've done the analysis with Clark subdifferentials to be able to prove stability and things like that. The alternative is to use Yoshida regularization or proximal methods. So we have derived all of the differential equations corresponding to various proximal methods and their accelerated versions. So here there are just some examples of what shows up. And again, we have derived the rates, and you get exactly what I was talking about. But what I wanted to go is, what about the other thing, which is, can I derive new optimization algorithms? And as it turns out, you can put this in the framework of Hamiltonians, particularly Hamiltonians of dissipative systems, where you begin, this here is the function you're trying to optimize, and then you add a kinetic energy. And these are the typical Hamiltonian equations. So now this can lead to new optimization algorithms because you can choose a different kinetic energy, and you can discretize these equations in various different ways. So if you take the classical kinetic energy, then you can show, for example, that classical momentum is symplectic. So it's a symplectic integrator for this equation. You can prove, for example, that Nesterov is not symplectic, and therefore it doesn't preserve some of the properties. And you can actually take now a different kinetic energy, like relativistic energy, and derive a new algorithm that comes from just taking this and applying a conformal symplectic integrator to derive that. We have applied this to neural networks. Here's a comparison of classical momentum and this relativistic gradient descent, this new optimization method, and showing that you get important acceleration both at training as well as at testing. So in summary, there is a nice connection between the dynamical systems, Hamiltonians, and optimization. And it's been extended to constraint problems, non-smooth, and you can get new algorithms via symplectic integrators for Hamiltonians of dissipative systems. And all of this is Guy, who is a postdoc in my lab. Thank you.
Thank you. Next is Daniel Park.
I'd like to thank the organizers for letting me talk about my work here. So I'm going to talk about the effect of network width on stochastic gradient descent and generalization. So this is work with Sam Smith, Joshua, who's obviously here, and Kwok Lei. Hopefully it'd be out on the archive next week. So the motivation for our work is we'd like to understand how to train smarter and train better. And it's to optimize this workflow. So given a task and a class of architectures, a standard workflow, at least for me, looks something like this. It's written in Python, the best language. So for all architectures, I loop over all architectures. Per architecture, I have a set of hyperparameters. I loop over them. I run a set of experiments with given architecture and hyperparameter and get a result. If I'm happy, I stop. If I don't happy, I move on. And I try to wrap it up nicely and present it at a conference like this. All right, so in the paper, we tried to help, we tried to make these loops smaller and trying to understand how far we should go and whether we can reduce the search space of hyperparameters. So I don't have time today, so I'll just do that part of the paper. I'm glad that SGD has been touched upon here already. I learned about this stuff in this paper, but obviously there are other works related to this. So in the small learning rate, so stochastic gradient descent is a gradient descent method where you take a mini batch, take the gradient there, and then descend according to that gradient. And so you have essentially two hyperparameters, the learning rate, which I call epsilon, and b, which is the batch size. And in the small learning rate regime, for reasons explained to us by Pratik Chowdhury, the level set of hyperparameters with respect to late time performance, say asymptotic accuracy, is essentially a level set of G. I'm calling it G. It's essentially the temperature. So this gives us already a big reduction of hyperparameter search space. So this plot is a particular, this is essentially the test set accuracy of a trained 3-layer network on MNIST. And I've plotted the performance test accuracy against 1 over batch size for all these different learning rates, right? So for a fixed learning rate, I plot over the batch size and look at what their performance at late time is. And they look kind of chaotic. But if I plot the test accuracy for all these different learning rates against the normalized noise scale, which is essentially this, you see a perfect fit, right? So essentially, your test set accuracy, your generalization performance is dependent on the normalized noise scale, rather than these two things separately. So you've reduced a big two-dimensional space into one. So you already see a big reduction here. All right, so as an aside, to compare learning rates across different networks, you have to kind of normalize them. The reason is that learning rates carry dimensions, scale like square in the dimension of the units of the parameters, so you kind of have to normalize them. Okay, so our goal would be to find the optimal noise scale, normalized noise scale for all these different networks, these different tasks for SGD across a linear family of models. So I'm going to look at various models where we scale all the widths up linearly. And I'm going to see, for these different sized models, how the optimal noise scale changes. That make sense? Okay. So there are 2 lessons learned by running all these experiments. The first is that the optimal noise scale is kind of at the stability bound. So if you plot, say, batch size or learning rate, the test accuracy against batch size or learning rate, kind of the peak is right before where training just becomes really bad, right? So the first main result is the optimal noise scale is like right at the point up to where training becomes very unstable. And it's true for ResNets, CNNs, and so forth. The other surprising result is there's this beautiful linear relationship between the optimal noise scale and the width. So this reminds us of the ideal gas law where temperature is proportional to volume, but no relation. But it's very interesting that once you kind of figure out the optimal noise scale for a single network in a family, you can essentially scale it up and get the optimal noise scale for other networks. So yeah, so there are microscopic rules for optimal parameters. These have implications on training. We should understand them, and we should generalize them to more realistic settings. And thank you.
Thank you. Questions?
So I have a question to the second speaker, Rene. Do you explain why this inclusion of relativistic kind of generalization can accelerate the training?
I don't think it has to do with the inclusion in particular. So there was one differential inclusion for something like subgradient descent, and there is another one for accelerated subgradient descent. So it's not the inclusion, the one that accelerates, but rather the use of second-order information.
Okay. Hey, Daniel, so for your experiments, what architectures do you explore?
Yeah, so we do ResNets, CNNs, 1, 2, 3 layer fully connected networks, and it works for all of them. We don't do any kind of regularization just to keep the experiments clean. We don't have a schedule.
But are these like with batch norm and like state-of-the-art
No,
architectures?
that's important. So if you add batch norm, the rules I just showed you kind of hold for ResNet still, but for CNNs it completely breaks.
Oh, interesting.
Yeah.
Do you know why?
No.
Batch norm makes the overall scale of the parameters, and thus the overall scale of the gradients irrelevant.
Right. But then we don't understand why it kind of works for ResNets, right? Yeah. So there's, yeah.
I have a question to the second speaker. Very short, naive question. So as far as I know, that as understand correctly, the ADMM is the alternating algorithm. Why does it converge into the one differential equation? How to say that consists by the two optimization problem, right?
Yes.
And the how to say, naively speaking, that converges into two differential equation. But
well, I mean, what you do simply is to, I mean, in the same way that you can write a derivative as xk plus 1 minus xk divided by the step size, you do that for the first order and the second order. So you need to just play with the equations of ADMM, that are two, and when you put them together, some of the terms cancel, and you still get a first order differential equation for classical ADMM. Yeah.
I'm just wondering, in the accelerated gradient descent, what you need an extra boundary condition for the second order term. What is that?
The velocity is 0. Yeah, x is equal to the initial condition, and x dot is 0 initially.
Oh, really? Is that sensible?
Why not?
Well, because you're already following the gradient. It seems strange to initialize with 0 velocity.
I mean, I don't think it matters when you have a problem that is convex how you initialize, because then you just follow the flow of the equations. But you're right that you could begin with x dot equals minus the gradient at the current. Yes.
What was the motivation for your new optimization strategies? I mean, you had a relativistic example and so on for the Hamiltonians.
I think the goal is to be able to generate algorithms that are potentially even faster or that have a smaller constant in front. And what the Hamiltonian framework gives is a framework for generating a large variety of algorithms by having a different choice of the kinetic energy. And so that was the motivation. But still the analysis of the stability and the convergence rate for that method, we have not done it.
Okay, I cannot see any more urgent questions. So let's thank all three speakers again. Okay, our next speaker is Rika Thomas.
So I'm a mathematician from the University of Washington, and I work at the interface of optimization and algebraic geometry. So I'd like to just illustrate to you an example of a more general phenomenon that you will see at this talk. So I'm going to talk about how you certify density inequalities in graphs as the number of variables goes to infinity. So graph densities are studied in a lot of contexts, in the context of large networks, statistical physics, and so on. There's a great book by Latsilovas, who was here at MSR for a long time, on large networks and graph limits. And the question is, if you have a very large polynomial that you need to certify as non-negative or certify an inequality, how do you do this, right? So the number of variables is going to infinity. So let me just illustrate this on an example. So here's a very famous theorem by Mantel in 1907. It's a theorem from extremal graph theory. It says that if you look at graphs with n vertices that don't have any triangles, then the limit of the edge density goes to half. So you cannot have more than half as many edges before a triangle will show up. Okay, so this is a classical result in extremal graph theory. So how do you certify such a result? So let me pose this as an optimization question. So what we can do is we can fix n, the number of vertices in the graphs, and let's look at all triangle-free graphs on n vertices. And my job is to maximize edge density. Okay, so I'm going to introduce a variable xij for every edge, and it's going to be 1 if the edge is present and 0 if the edge is absent. Okay, so if I want to maximize edge density, well, I sum up all the edges. That's sum xij, divide by the total number of edges possible, which is n choose 2. So that's the objective. These xij's are 0, 1 variables, so I have these equations. Xij square is xij. And I don't want any triangles, so I want xij, xjk, xik to be 0. So one of them has to be 0. You can't have triangles, okay? So this is a polynomial optimization model of how you maximize edge density over triangle-free graphs. So our job now, Mantel's theorem says that the limit of this objective function as n goes to infinity is half, okay? So how do you certify something like this? The number of variables is going to infinity. So it's really enough to do this, right? We can take half minus the objective plus a small error that's going to vanish as n goes to infinity, and we can certify that this left-hand side is not negative on all triangle-free graphs, okay? So all of optimization, in my view, is certifying non-negativity. That's just the way I think of optimization. So our idea to certify this left-hand side as being non-negative is one way to do this is to write it as a sum of squares. This is a very classical method, goes back to Hilbert in the 1800s. And the problem with writing things as sums of squares is that sums of squares requires you to write your left-hand side as a vector of basis of the vector space that you're working with times a positive semi-definite matrix times that basis again. So if your vector space is infinite, the basis is infinite, and this is going to be very difficult. So here's how you do it. So the first step is you notice that these objective functions are symmetric. So they're highly symmetric. In this case, the symmetry of the symmetric group acting on this. So under that, there's a very nice result by Gautam and Perillo that says that your sums of squares is going to break. So the positive semi-definite matrix that you need is going to block diagonalize. And each big block is represented by one irreducible of the symmetric group. And it further breaks into little blocks, and the little blocks in one block are all the same. Okay? So you only need one of these colored blocks per irreducible of the symmetric group. So that's result number 1. But still, as the number of variables goes to infinity, this matrix goes to infinity, and you're going to get infinitely many blocks. Okay? So the next and final step is to argue that most of these blocks are going to be absent. So if you fix the degree in which you want to certify but let n go to infinity, you will only get a couple of these blocks or a few number of these blocks that actually show up. So the sums of squares expressions you write are very, very finite. Okay? They're very small, even though the number of variables is going to infinity. Okay? So this is just an example of, in the presence of symmetry, you can actually certify these infinite functions, they're actually functions that were on the left, by using representation theory to cut down the number of expressions that you will get on the other side. So that's the result. So fixed degree, one can recover sums of squares expressions from standard symmetry reduction techniques for symmetric non-negative expressions over hypercubes in this case, even as the number of variables goes to infinity. Thank you.
What we do in physics is we have a lot of messy data. And within this messy data, we try to find simple variables, variables which are related by simple and clear equations, like this. And of course, there's a lot of other data which are correlated or meaningful in other ways, but not as clean as this. And those are still there, but we don't want them. We give them to biologists or other fields. And then if we're ambitious, then we want to solve these equations. And what that means is we want to find variables which uniquely specify solutions, independent solutions. So these independent variables we call phase space. So it's very close to what people are trying to do in unsupervised learning, where they are trying, for instance, to take a big database of faces and identify some independent parameters which are important in characterizing the faces, right? Like this, are they smiling? Is a person an Asian or not? So these would be like these independent variables of phase space. Right? So one way that this is done, for instance, is using a variable autoencoder, where the data is given by a random variable x, and you compress the data to obtain some intermediate representation z, and with some clever loss functions trying to make sure that z contains these independent variables. And this has been used, this can be done also with two different data. For instance, suppose you want to correlate the past to the future and find the explanation that allows you to do this connection. And this has been done, for instance, to try to extract laws of physics from data by these people. I want to propose a very different way to do this, inspired by some work from renormalization theory, where we are given these two data, x and y, and we're trying to find the correlations between x and y, and we plug them into two parallel independent neural networks to extract variables f and g, and you should think of f and g as being these variables of x and y which are most correlated, which contain most information about each other. And then there are direct equations that relate this f and g, and there's also a lot of algebraic structure within each of those variables, which but it's still ongoing work to characterize them. And the objective for this is something I call relevance, which what those things are is they are covariance matrices between these features f and g. And what this does effectively is a singular value decomposition of the conditional probability distribution, which is a linear map on the space of probabilities over x and y. And so these f, they describe subspaces in the space of probabilities. To do an SVD, we need a metric, and here I use an information metric, which is a chi-square metric, which leads to this very nice expression. And this expression is very easy, very fast to optimize, so it works very, very well. If you only have one type of data, not two types of data, you can also just input by hand a conditional probability to output y from x. And what this does is it kind of indicates to the system what you consider to be important or not in a broad sense. For instance, and this is how this thing was developed initially in physics, is to understand renormalization, to have a model of renormalization where I start from a spin system, and this corresponds to a blurring, so it destroys small-scale information. So I'm telling the system that I don't care so much about small-scale information. You can also think of this as introducing a metric on x. And then when I apply this system, this algorithm, I find in F will give me an algebra of the field operators that emerge from the spin system. So I don't have time to give you examples, but you can check the paper. Thank you.
Thank you. You had 1 minute left, so tell us 1 minute about the example.
Okay, so I'm glad I put it. So I can apply this to supervised learning, and it converges much faster than standard approaches, at least in one model I've tried. So if you want to try it on other models to see if it's always converges that fast, you should try it. Here it generates the left half of the MNIST digits from the right half. It generates, so what it does, it allows you to get the expected value over the posterior. So these are blurry because this is an average of all possible guesses of the left half of the digits. And one can also explore the variance in the direction with the most variance in the posterior distribution when you do Bayesian inference. So it allows you to, so it does not allow for sampling from the posterior, but it allows to compute expected values of any function of the posterior. And I guess I don't have time for this. I suppose.
All right, thank you. Questions?
This is a question for the second speaker from Facebook. I was just wondering, in your examples, I didn't see the advantage of hyperbolic space over a tree. I wonder if you could explain that.
So why use a continuous representation, not a discrete?
Well, in your examples, you went up to the hierarchy until there was a branch point, and then you descended down to this specific example, like the Burmese cat. And so your examples illustrated navigating a tree for represent distance, and instead you spoke of hyperbolic space, and I wanted to know what the advantage was to modeling the tree structure as within a hyperbolic manifold.
So what I showed you was if I go along the geodesics in that space, so I have my golden retriever and my Burmese cat, I have my embedding of that hierarchy, and I go along the geodesics of that space, what would be the points that I cross in my original data set? So I assume I don't have access. For instance, in word embeddings, I typically don't have access to the structured data, but I want to uncover it. So if I do something like I try to learn word embeddings on a text corpus, and I want to learn some hierarchical structures from the co-current statistics, for instance, in the data set. This would be applicable in that case, where you say, well, I learn my embeddings, and if they kind of capture somehow the ontological or taxonomical structures in the embedding space, this is nice because now I can use this for knowledge discovery, for instance. And this was the idea to show, well, if I know the ground truth tree, can I show you that I can actually recall that in the embedding space?
And just related to that, in order to have an apples-to-apples comparison between hyperbolic and Euclidean embeddings, you really should supply the length scale in hyperbolic space, since the volume grows exponentially.
I'm sorry.
Well, the difference between embedding and hyperbolic and Euclidean space is only apparent at a large length scale. At a short scale compared to the curvature, there's basically no difference. So if you say that it's better to use hyperbolic than Euclidean, you really have to kind of tell us the radius that you're using within hyperbolic space. And then the comparison shouldn't be between 200 Euclidean dimensions and 5 dimensions of hyperbolic space, but rather it should be the volumes, respectively, that are involved.
Well, no, so the dimensions are actually very important because if I take, so one of the reasons why we cannot scale graph embedding sufficiently anymore is because I need too many dimensions in my embedding, in my Euclidean embedding, to do this on large-scale graphs. So if I have a graph with, 100 million nodes, and I need to have a 1,000-dimensional embedding equation for the 1 million nodes, that just doesn't compute anymore. It's very hard to scale. So, but if I know that my graph, for instance, has a tree-like structure, and I can embed that graph efficiently in 5 dimensions, that's a huge game, because now I can handle graphs and model them very efficiently in a low-dimensional space. And for that reason, the dimensionality is really very important for computational reasons.
One of the striking things about the current word embeddings are these superposition equations, like king minus man plus woman equals queen. Did you try checking for that?
No, I didn't try analogies yet. It would be interesting, but I don't know what kind of analogies are in that space, actually.
Hi, thanks all three speakers for your talk. My question is for Rekha. So your talk was on the Boolean cube. Can you comment on other domains that you can scale this method on, like the sphere or something?
Yeah, certainly. You can do sums of squares over any variety, not just the Boolean cube. The Boolean cube is a finite variety. It's just that for every case, you would have to understand how the representation theory works on the vector space that you're working with.
Right. So I'm talking about like practically, if you want to implement an algorithm that's efficient, on what kind of domains can you scale this up to? So to actually make it practical, there's still several more steps that you have to worry about. So it's not quite at that point yet, but I think the point is simply to say that it's even doable, that it's actually finite. I see.
At the moment.
All right. I can't see any urgent questions anymore, so let's thank all three speakers again. And next up is Paul Smolensky.
Thank you. The work I'm going to talk about is very different from all the other talks we've heard so far today. I'm a cognitive scientist, proud of the fact that so many of the ideas that fuel deep learning today were actually brought to light by cognitive scientists trying to understand how intelligence arises in a brain. A key distinction in our field is that between mechanism and function. Functions like mechanisms can be defined very precisely, such as the way grammars define language functions. And a popular strategy in the field is to work top-down, starting with a functional analysis of the task, which can then inform the design of, or the reverse engineering of mechanisms for performing the task. So I'm going to introduce a very high-level overview of a case study to show how theories of cognitive function inform and are informed by neural network theory. Mainstream theories of cognition have always deployed symbolic computation, in which we have capabilities such as all of these. How are these implemented in the brain? Well, the picture that we pursue in this work is that the symbolic computational description of what goes on in the mind is a higher level description of a neural network, and that we can understand the relationships there just the same way we do in physics between macro and microstructure. The work rests on a kind of quasi-isomorphism, using the term a little bit loosely, in which we view a symbol structure, like a tree, as a set of roles, the places in the structure where symbols can fall, and the things that fill those roles, typically symbols or more complex structures themselves. So if we look at a symbol structure at this level as defined by a set of roles, each filled by a certain symbol, say, then that gets mapped down to an activation pattern, which is defined in terms of vector embedding of the fillers or the symbols and vector embeddings of the roles that they play in the structure. This is called a tensor product representation, inspired by the way that electrons contribute as parts to the structure of an atom as a whole. Using these kind of representations, it turns out that neural networks can exactly implement recursive function computation, although it's done in a massively parallel way, not in the way that it has traditionally been done. And as far as processing is concerned, in the networks that we study, we use a dynamics that is characterized by a Lyapunov function. It maximizes a function I call the harmony, which is negative energy in Hopfield's terms. If you assume that the activation pattern here is in fact a tensor product representation of a symbol structure, then you can pull the harmony, or the energy of a pattern of activation here up and use it to define the harmony of a symbol structure. And the computation of the harmony can be computed entirely at the symbolic level in terms of what then becomes called a harmonic grammar, which consists of a bunch of constraints about which constituents are well-formed when they combine in the same structure and which ones are ill-formed. This led through empirical observations about natural languages to a variation of this theory called optimality theory, in which the constraints that characterize the energy function at the symbolic level are universal, the same in all languages. They interact by a non-numerical interaction called strict domination, in which we have a ranking of these constraints from the highest priority to the lowest priority, each one having absolute priority over all the lower ranked constraints, which gives us a way of formally computing typologies of possible human languages. So that allows us to formulate a set of universal constraints as a hypothesized grammar, compute by hand or with software the space of all possible languages that can arise from the rankings of those constraints, and thereby give one of the very first formal methods of studying cross-linguistic typology and linguistics. In current work, we're using deep neural networks, which are biased to use tensor product representations in their hidden layers. This leads to greater interpretability and improved performance, and we hope eventually to networks that can learn the kind of symbolic knowledge that we know is very powerful in higher cognitive domains, such as reasoning and language. Thank you.
Next up is Pengjuan Zhang.
Okay, so today I will talk about deep generative networks in Bayesian inverse problems. So here I talk about Bayesian inverse problems, but you can just think about its Bayesian inference. So this is a collaboration work with my previous PhD lab, so from Caltech. For Bayesian process, it's a very beautiful framework for inverse problems. It can combine the prior knowledge, the physics, and the data into together to do the inference for use. Especially, it can make use of small data. Currently, deep learning it's good at big data, but not good at small data. But it also has some limitations. For example, it's difficult to obtain high quality samples from the posterior, especially when the dimension of the S space is really high. So this is called the curse of dimensionality in the Bayesian inference. You are really difficult to samples from the posterior. So there are several approaches to to deal with the curse of dimensionality in this case. For example, we have MC-MC algorithms. That's the standard popular method to do that. But MC-MC has several different variants, variants like the HMC, the Hamiltonian, Monte Carlo, and Mana, many other variants. But MC-MC type method suffer from some disadvantages, like it has no mixing rate. You really need to define the topology of the random walk really well to really make it work. But as the dimension goes down, you know that no matter how you define it, it's very difficult to mix. And also, you do not know when to stop the MC-MC sampling because there's no really a clear stopping criteria to say that, okay, you reach the stationary distribution. There's also another path of research, like the transport map to deal with this problem. The idea is just, okay, I will learn a transport map from a simple distribution to approximate the target's posterior distribution. The method in this group, we have the implicit sampling from Choi's group and some optimal transport maps from MIT group and many other works. Currently, still, I think MC-MC method dominant because really this transport map still suffers from curse of dimensionality because how to parameterize these transport maps, it's really a difficult problem. So the idea in my talk is very, very simple, just this sentence. So we want to use deep generative networks as transport map to approximate the posterior distribution. So the reason why we want to do this is because, first, in the deep learning community, recently the GAN generative adversarial network achieves quite big success in approximating the distribution of natural languages, natural images, this kind of thing. So it shows that the deep generative networks has huge capacity to really approximate high-dimensional distributions. Why not we use this to approximate the high-dimensional posterior distribution? But there's also difficulty in this one. So the difficulty is that the density of the generative distribution is not computable. So the maximum likelihood does not work. In fact, this sentence now is not true anymore. This is not is true for my research last year, but this year I kind of changed it to design invertible deep generative network. So the density map is computable. So in fact, then we can do this kind of maximum likelihood type analysis for this one. So this is kind of the idea. So for Bayesian inference, you have prior, you have likelihood, and then you have posterior. What we want to do is really you learn this transport map, the deep generative network, to transport from a simple distribution, for example, Gaussian, to approximate the posterior distribution. And what we need is the density function of the generated distribution. In this case, we need the determinant of the Jacobian of the inverse of the generative network. So this is kind of, this is the idea, and this is typically the method we want to use, but there's a lot of things to do the architecture search of the deep generative network and also the loss function we want to use here. But because of time, let me just show you some results. For example, here we want to approximate a 16-dimensional distribution, high-dimensional distribution. We can do even thousands of dimensions, but let's just show one simple example. So this distribution have multi-modes. Multi-modes is the topic in Bayesian inference, and the MC is difficult to capture. So you can see that when we when we project this 16 distribution into four-dimensional distribution, we can clearly see this multi-modes. This is kind of the distribution of the first projected coordinates. This is the second one. You can clearly see there are multiple modes here, and these are the original coordinates, 16 coordinates, and these are the covariance between any pair of these coordinates. You can clearly see that there are multi-modes here. And these are the distribution we learned from there. So you can sometimes you can see that by quantity we capture all the modes, and in fact for some small structure, for example here, this is a multi-mode, and you can see this one have multi-modes, and we capture this one. We captured this multi-mode. We want to emphasize that in the Bayesian setting, we do not have access to the IID samples of the posterior distribution. There's a main difference between the GAN work, the traditional machine learning work, and the deep generative networks in Bayesian inference. But we succeeded to really, without IID samples from the posterior distribution, we succeeded to still learn the multi-modes. So, which means that our deep generative network can explore this space to to get the different modes by itself. We want to solve. Okay.
One sentence.
Yeah, one sentence is that here the simple idea is just we propose deep generative networks as transform map to approximate the posterior distribution, and what we think that the Bayesian inference is a powerful framework to combine the prior knowledge, physics, and small data, and we want to explore deep learning's capacity in this region.
Okay. Thank you.
Thanks for staying for that long to hear my talk. So this is a quantum machine learning talk with some practicality intent, believe it or not. It's a generalization of some research done by a few researchers in quantum architect and compilation group. Maria Schuld is with the University of KwaZulu-Natal. She done a lot of work while interning with us. quantum machine learning first, and then we dive very quickly into the specifically classification. So something happened in the year 2008. Haru, Hasidim, and Lloyd invented a breakthrough algorithm for quantum linear algebra, and later many known the quantum machine learning technology has been quantized using this algorithm. But then reality check came in the last 3 years or so, where it turns out that to actually do this on a quantum computer, you need a very large quantum computer, which is very well error corrected. Right now, there are some offerings for the so-called noisy intermediate scale quantum computers, which are about 100 to 200 qubits, not error corrected. Our proposal is one of those recent proposals. There are not too many of them. So let's look at the conceptual. In fact, there will be a couple of slides which are almost purely conceptual. So what do we want to do for classification? We want to have a data. We want to do some quantum processing, which is massively parallel processing. We want to measure some observable and get out a class label of the data from that measurement. Specifically, in quantum computation setup, what this means is we take some data and we expose it to a so-called variational quantum circuit, which is a circuit consisting of some quantum gates and parameterized in a certain way. And we want to learn those parameters such that after some measurements, we get the highest probability of getting the correct class label out. So this is obviously supervised learning exercise, and our goal is to learn those parameters in a variational quantum circuit. So a little bit of mathematics here. Suppose that this is a binary classification problem, and we have an observable with two eigenvalues. I arbitrarily assume that one of the eigenvalues is greater than the other. What we want to maximize is the probability of measuring the correct label here. This expression is not as scary as it looks. So basically, this is summing up over one class of the probability of measuring correct class label for the members of this class, and this is summing up the probability for the other class. And of course, we want to maximize this probability. So a nice physical observation is that this is actually equivalent to minimization of an energy gap between the two classes if we consider this guy here, which is adjoint of the observable with the variational circuit we want to learn, right? So if we call this Hamiltonian, then this would be an energy gap between two classes, and we want to minimize it. So it turns out that you can, for example, apply stochastic gradient descent for this kind of task, and it actually works. The interesting thing is that it's not the gradient of these guys can be computed analytically, assuming that the gates constituting the variational circuit that we want to find are analytical. So, summary. There are some distinct advantages of this approach. First of all, variational circuits allow for compact classical parameterization, so you can actually keep tally of the parameters classically. And therefore, they allow for quantum classical training, which means that the quantum computer is only inserted for computing expectations and not for actually telling the gradient descent details, for example. This is resilient to noise, both label noise, parameter noise, and gate noise. And it doesn't put a huge onus on the fidelity of the qubits and gates. And therefore, this technology is suitable for the NISQ era, not noisy intermediate size quantum. We have validated on some classical benchmarks. For example, MNIST you can do on 8 qubits. Well, it's not the best MNIST classification quality, because what I want to tell next, and this is outside the slide deck, is a couple of limitations. First of all, geometry I just shown you of the quantum circuit only traces well the quadratic, so the polynomial boundaries between classes. If you don't use ancillary qubits, like 8 qubits for MNIST, then it can only assume quadratic boundary between classes, and this gets you within 1.5% on the MNIST. So it's not the best performance ever. If you double the register size, if you triple, then the degrees of polynomial will go up. Another limitation, which is not relevant to MNIST but is relevant in general, is the number of parameters you want. The number of parameters you want is related to how much you can reduce the dimensionality of your feature space without losing the representation power. Let's say if you can do a PCA and reduce dimensionality of your feature space to 100, then you roughly need 100 parameters in the quantum circuit, and this kind of shows the depth. Sometimes you cannot reduce parameter space much, and in this cases, which I do not know what those cases are, but you can invent one synthetically. You don't have any quantum advantage at all. I mean, it will have maybe a quadratic advantage, but not exponential advantage in the number of parameters. With that, I wanted to say thank you. So the paper that analyzes various things, including MNIST, is Maria Schuld and others. Unfortunately, I didn't put the archive number in here, but this is easily discoverable on the archive.
Thank you very much. Time for questions for all three speakers.
I want to ask one question to Alex. So in the case of quantum computers, that loading the classical data requires linear in the number of data size, right? So how can you beat the classical computer by using quantum computer? Because there is an overhead, right? Loading data.
Well, you cannot beat it here. The only advantage for this approach on the classical data is the number of parameters. So you get smaller model sizes, both in width and depth, right? You don't beat it in training time or anything. But another advantage, I'm not sure if I listed it here, is that you can actually entangle it with a quantum device and do machine learning on quantum data without need to first massively extract classical information from the quantum state. So basically the main use case for this is training on quantum data proper, which is a quantum like from the beginning, right? Okay. From the get-go, and you don't have to prepare the states.
Actually, you already answered my question. Thanks.
Okay.
I have a question until the walkthrough. So about the GAN networks, so are there any particular network structures you're looking at, or are they kind of standard GANs? And what kind of loss are you using?
Oh, yeah. So that's really the research topic there. So here, in fact, if you naively use take some off-the-shelf invertible network, it will not work. The essential idea that it can capture multi-mode is that we design a multi-stage generative network. You first approximate the you can think in this way: when you approximate an image, you first approximate kind of a very coarse grained image, very low resolution image. you do the approximation in this no-dimensional space well, and then condition on this no-dimensional space, you can add more details there. So we kind of realize this idea into design of the multi-stage generative network, and that's invertible. In this way, in fact, we can capture the multi-mode. The loss function we use is both scale that you have the distribution your generative network offers you, and the distribution of your targets, the density of your target distribution. We have the K divergence between them and the inverse K divergence between them. We use both to do that.
My question as well is, so you're not doing a GAN setup where you're using data to train your thing, right? So like you have, I guess, some unnormalized probability function.
Yeah,
so how are you doing the training? What's the trick?
Sorry?
What's the trick to, since you don't have the closed forms, you can't sample from the target distribution?
Yeah, so the trick is that first we use like this double K divergence as north. So one direction is very easy because you can sample from your generative network and evaluate on your density. So this part is easy. The other part is not easy. You cannot sample from your target distribution and evaluate on your generative network. Then in that way, what we do is we use importance sampling. And the importance sampling, the proposal of distribution is really the distribution from the lower resolution approximation, so that we have a good importance sampling distribution.
I see. Interesting. Thank you.
Further questions? Okay, I can't see any more questions, so let's thank all three speakers.